All right, on page 370, in that first section, you are just going to convert from logarithm to exponent. So the first one says 370, log base 81 of 3 equals 1/4. What is that in exponential form? 81 to the 1/4 is 3. Okay. In the next set, you're doing the exact opposite. So 0.00001 equals 10 to the negative 5. What is that converted into logarithm? So it's log base 10. So I'm just going to write log. Log of 0.00001 is negative 5. Okay. Now the next set says evaluate the logarithm exactly. Log base 2 of 1 equals what? How do I solve that? I use the formula called change of base. I don't have log base 2 on my calculator, so I just do the ln of 1 over the ln of 2. Oh, that won't work. Sorry. ln of 1, you got to close the parentheses, divided by the ln of 2. And the answer is 0. Okay. And then in the next set, 55 through, well, in that set right there, state the domain and the range of a log function. And I'm skipping all of the graphing logs in this chapter because we just don't do it. We don't graph. But logarithms are the inverses of exponents. So all exponential equations have the x-axis as a horizontal asymptote. So if you have an exponential growth equation, it's going to look something like that. Okay? If we have an exponential decay, it's going to look something like that. Right? The steepness might change, the y-intercept might change, but the direction will always be the same. If we start using negatives, like e to the negative x or negative e to the x, we start to get graphs that either look like this or like this. So all exponential equations have the x-axis as a horizontal asymptote. Right? All logarithm equations have the y-axis as a vertical asymptote. So it could look something like this, or something like this, or something like this, or something like this. Wow, that's pretty. It is. It's a the Christmas tree star. So we can also transform logarithm graphs. We could slide it to the right or to the left, or we could slide it up or down. But all logarithm equations will have a vertical asymptote and some sort of domain restriction. What I mean by that is every basic logarithm is going to look something like that. Now it could be one of the other forms, but it will have the y-axis as a vertical asymptote. But we might be moving that up or down, or we might slide it left or right, in which case the vertical asymptote moves. But you can see that every logarithm graph has a domain restriction. Right? There's some point where none of these x's work. So in this particular graph, none of these x's are part of the domain. Yes. So you could also have one that looks something like this, in which case all of this is not part of the domain, and we already know what happens to create that, and that's when you have a negative inside a logarithm. So if I have log base 2 of x minus 4 and have y equals, what numbers can I not plug in? Anything 4 or below. What's wrong with 3? Why does 3 not work? 3 plugged into the x would give you 3 minus 4, which is negative 1, and you can't take the logarithm of a negative number. Now, if this number is negative, then that's not totally true, but that's never going to happen. You will never have a logarithm with a negative base because those graphs are not continuous. They end up bouncing all over the place, and we just don't do it. So for the purposes of this class, the base will always be positive, and it will always be, it's never going to be 1. Can't be anything 0 or smaller, and it's not going to be 1, because that's just a horizontal line. 1 to anything is 1. So what we do is look at the logarithm and say, this stuff cannot be negative, and it can also not be 0. So we say, x minus 4 must be greater than 0. And then we just solve for x. So x is greater than 4. Because anything less than or equal to 4 creates a negative on the inside. Okay? What about y equals log base 8 of 5 minus 3x? Well, I know that this has to be a positive number. So I write 5 minus 3x must be greater than 0. Subtract the 5. Negative 3x is greater than negative 5. Divide by negative 3. And I get x is, flip the sign because I divided by negative, less than 5/3. So now in this case, 2 doesn't work. If I plug 2 into the original formula, 5 minus 3 times 2 is 5 minus 6, which is negative 1, and you cannot do that. Now, these are not imaginary numbers. Right? This isn't a set of numbers that just don't lie on the x-axis. These numbers flat out don't exist. Right? There is no way to do it. You cannot create a negative number with a positive base. It's like saying 2 to what power is negative 16? You can't do it because all you're doing is multiplying by 2. And no matter how many 2's you multiply, you cannot create a negative number. Okay? Why do we flip the sign when we multiply or divide by a negative? Well, because, well, let me show you 2 different reasons. First, if I add 3x, then I get 5 is greater than 3x, and then you can see 5 over 3 is greater than x. That's what we got. It was just kind of rotated around, right? Well, the reason that's the case is we no longer have a balance. If I had some sort of scale, and I had a bunch of weight on this side, and a bunch of weight on this side, and I times everything by negative 1, that means I turn every downward push to an upward push, right? So let's say I had 16 pounds over here and 16 pounds over there. So instead of pushing down 16 pounds, when I multiply by negative 1, I'm going to put a big balloon here that pulls up at 16 pounds. And this one also pulls up at 16 pounds. Okay? But if the inequality is inherently unbalanced, so this is saying that the left side weighs more than the right side. So I'm looking at something like this, where I have 8 pounds here and 5 pounds there. What happens when I turn those downward weights into upward weights? Well, if I turn this into a balloon and I pull up at 8, and this is a balloon and I pull up at 5, what's going to happen to my balance? It's going to flip the other way, which is why we need to switch the inequality every time we multiply or divide by a negative. Does that make sense? Yeah? Okay. Look back at that logarithm problem. What did the base have to do with the domain? Absolutely nothing. So when you're looking at the domain of a logarithm, the base doesn't matter. The base has no, as long as the base is a number and not a variable. So all we have to do is take the stuff in the parentheses and set it greater than 0. Well, what if the stuff inside is a quadratic? Y equals the log of x squared minus 4x minus 5. Well, let's factor that. I have x minus 5 and x plus 1 must be greater than 0. Right? So I know that x equals 5 and x equals negative 1. Okay, but can x be 5 and can x be negative 1? It can't be either one of them. How come? Because when I plug in 5, what happens is not negative, it's 0. So if I plug 5 in here, I end up with 0. Can you take the log of 0? No. Okay, same thing here. But what we're looking at is a graph that looks like this. Right? So this particular number doesn't work because when you plug it in, you get 0. And this particular number doesn't work because when you plug it in, you get 0. But some numbers will work, and some numbers won't. Looking at that parabola, which numbers can I plug in and which ones can I not plug in? Can I plug in x equals 2? Why not? When you plug in x equals 2, your answer is negative. Or, so I can plug in all of these numbers and all of these numbers. Because when I plug those in, I end up with a positive y value. So 2 doesn't work because we get some sort of negative number. If I plug in 2, 2 squared is 4, minus 8, minus 5 is a negative number. Okay, will 3 work? Nope, when I plug in 3, I still get a negative number. 4, I get a negative number. 5, I get 0, but 6 will be positive. If I plug in 6, I get 36 minus 24 minus 5, which is 7, and 7 is a positive number. Does that make sense? Anybody not understand how that works? So I looked at the graph and figured out which ones work and which ones don't. Let's say I had log base, it doesn't matter, of x minus 3, x minus plus 1, and x minus, nope, let's say plus 4. Well, this is a graph that hits at negative 4, negative 1, and 3. And it looks like this. Which numbers can I plug in? So it's a 4. So x can equal negative 4 to negative 1. Can it equal negative 4 or negative 1? No, because those give us a 0, and you can't take the log of 0. And we'll union that with 3 to infinity. Does that make sense? Because though, and I don't even care what they equal, right? So all of these numbers create negative answers. And the weird thing is I don't care what the numbers are, what the y values are. All I care is that they're either negative, or sorry, either positive or not positive, 0 or negative. Okay? So all of these numbers will work, and all of those numbers will work. Does that make sense? Okay, what about this? What would the domain of that be? Ah, where does this graph hit the x-axis? It doesn't. So all we need to know is, are all of the answers positive or are all the answers negative? They're all positive. No matter what number you plug in, you'll get a positive number, which means the logarithm will work. So this has a domain of all real numbers. Yep. If you have so if you have any sort of absolute value, 2x minus 7, what does this do to the stuff on the inside? Makes it positive. 0. Good point. 0 you can't do. So you need to find out, when does 2x minus 7 equal 0? That would be 7 over 2. So that point doesn't work. It would be everything except 7 over 2. That's a good point. I totally overlooked that. Well done, Jimmy. Okay. What about this? Negative absolute value of x. Nothing works. Because every number that comes out is negative except one of them. And that's 0, and 0 doesn't work anyway. So that is a graph that does not exist. I wonder what the calculator would do if you plug it in. My guess is a calculator is just not going to graph anything. It won't give me an error, but it's going to explode. So the log of negative absolute value of x. It's math, and then you go over one column to number. So it's going to, when it's done graphing, I can push trace, and no matter what number I plug in, I get y equals nothing. So if I go to the table, I'll have nothing but errors. Yeah. So I did log of the negative absolute value of x. And it didn't give me an error because I never divided by 0. Right? But, yeah, the table is a bunch of errors. But there is no number that works. So this has no domain, which means the function does not exist. Or you could say it exists in a vacuum. Vacuously true. Those are really fun proofs. So a vacuously true proof is something that is true in a vacuum, in an empty space. For instance, I could say all people who are 12 feet tall have green skin. And then my proof is there is no evidence to the contrary. There is nobody 12 feet tall, so you can't prove that it's false, therefore it's true. That is a right. So that would be called being vacuously true. It's true in a vacuum because there's no counter example.